methods should yield the same age on the same rocks. The reason is because the different parent-daughter atom pairs are supposed to be dating the same geologic event, that is the formation of the rock, the original volcanic eruption, for example, of the lavas. So the different dates have to mean that the parent atoms or isotopes have decayed at different rates in the past compared to today's measured decay rates over the same time period since the formation of these rocks. So what does that mean? It means that the uranium clock has ticked faster than the potassium clock, which is why the uranium gives you an older age than the potassium. It's ticked through many more supposed millions of years than the potassium clock since the rock formed. If they both started at 0 times 0 with no daughter, one is ticked faster than the other through the same time period. The decay rates have been much faster in the past. Radioactive decay rates therefore have not been constant, so none of these dates on any of these rocks are the correct age for them. So in general, we found the slower the present decay rate, the more decay was accelerated, so the resultant ages are older. So for example, the uranium decay rate is slower today than the potassium decay rate. In all of these examples, we found that the uranium ages of the rocks were older than the potassium ages of the rock, which means that the uranium had decayed more rapidly through the same time period than the potassium to give the older ages. And this is the systematic pattern we saw when you plot all those together. The uranium, lead and samarium, neodymium or alpha decay ages were always older than the potassium, argon and rubidium, strontium or beta decay ages. And sometimes the longer the present half-lives, the older the ages. That is, the slower the present decay rates, the older the ages. We also found this relationship, where the heavier the parent atom, the older the age. The heavier the parent atom, the higher the atomic weight, the older the age. Now, we don't know for sure yet exactly what causes this accelerated nuclear decay in the past, which would have to have been during the flood, for example. We don't know yet what mechanisms may have done it, but we do know whatever mechanisms were involved, they were probably at the nuclear scale, because the alpha decay gives different results to the beta decay, and it has to do with the atomic weight, which is in the nucleus of the atom. So it's what was going on inside the nucleus. And Eugene Chaffin has suggested it has to do with the binding forces that hold the nuclei together in the atoms. That there was changes during the past in the flood which causes these accelerated decay rates. Now, why would God allow nuclear decay to accelerate, say, during the flood? Well, the major byproduct, apart from radiation from nuclear decay, is heat. What drives geological processes? Heat. And what happened during the flood was very largely driven by heat that came from inside the Earth, when you had molten material coming up from inside the Earth. The alpha decay ages are always older than the beta decay ages. Often the heavier the atomic weight, the older the age. So how reliable is radioactive dating? We've now seen that even assumption 3 is violated by accelerated decay rates. So let's sum up. We're going to talk about this in the next talk. There's actual physical evidence of radioactive decay in granites called radiohalos. We'll talk about that in a moment. Here's a granite inside a granite, and we actually see physical evidence of radioactive decay. And I'm going to explain this in the next talk after the break. This is where the radioactive decay has damaged the crystals. And you can see these. Now, I don't understand why this is here. I thought I'd chop this out. Something's gone wrong here, because I was going to go straight into the conclusions. So let me just go through all of this. Okay, summary and conclusions. I know what I was going to say, that's right. That's okay. When all four major radioisotope clocks are used to date the same samples from the same rock units, they invariably yield different ages. The different ages can be explained if these radioisotope clocks ticked at different, faster rates in the past than the slow measured rates we see today. The three assumptions of radioactive dating are violated by inheritance, by contamination, and by accelerated decay rates. So if the assumptions are violated, then the very methods themselves cannot be trusted. And what I will show in the next lecture, the next talk, is the concurrent formation of two different types of these radioactive halos, radiohalos, are observable physical evidence that there has been abundant accelerated radioisotope decay in the past. And so we'll talk about that in a moment. Thus, the radioisotope methods for the dating of rocks are highly unreliable, and since radioisotope decay rates were grossly accelerated with hundreds of millions of years worth of decay compressed into only days, the Earth may be young, in fact only thousands, not billions of years old. And I close with this quote. This comes from the technical scientific literature. As it is impossible to distinguish a valid isochron from an apparent isochron in the light of rubidium-strontium isotopic data alone, caution must be taken in explaining the rubidium isochron, the age of any geologic system. And he concluded, in conclusion, some of the basic assumptions of the conventional rubidium-strontium isochron method have to be modified, and an observed isochron does not certainly define a valid age information for a geological system, even if a goodness of fit of the experimental data points is obtained in plotting the strontium versus the rubidium. This problem cannot be overlooked, especially in evaluating the numerical timescale. Similar questions can also arise in applying the samarium, neodymium and uranium-lead isochron methods. So even in the technical scientific literature, we have doubts cast on these dating methods. Thank you very much.